In this last video for Chapter 7, we're going to look at the two so-called hyperbolic functions, y equals sine hx, the h standing for hyperbolic, which is defined as e to the x minus e to the minus x over 2, and the corresponding cosine hyperbolic cosine hx, which has a very similar definition to e to the x plus e to the minus x over 2. Let's look at the graphs of these two functions at the bottom of the screen here. So you can imagine that if you add the exponential function e to the minus x, or actually e to the x, with the decay exponential function e to the minus x, that it makes sense that you would get a graph that looks like this. And you can imagine that if you take the graph of e to the x and subtract from that e to the minus x, which is the same as adding minus e to the minus x, so e to the minus x looks like that, but minus e to the minus x would look like this. And so if you add these two functions together, it should make should at least make pretty good sense that you would get this sine inverse graph here, and that's contrasted with the cosine inverse graph, or I'm sorry, cosine hx is the green and sine hx is the blue. Now what about the derivatives of these functions? So if we take the derivative of cosine hx, so y equals cosine hx looks like this. If we take its derivative, we get y prime is e to the x minus e to the minus x over 2. So the derivative of the cosine hx is the sine hx, and then if we take the derivative again, we get back to that, right? So y double prime is back to that. So let's examine this function right here, the cosine hx, by rewriting it as, or by factoring e to the x out of the numerator to give us, what, 1 plus e to the minus 2x over 2. And we want to analyze it with respect to its signs when x is less than 0 and when x is greater than 0. So here in this picture is the graph of e to the minus 2x, and if you look in your textbook on page 155, you can see this graph. What's important about it is that that when x is less than 0, e to the minus 2x is much larger than the graph of the equation y equals 1. And so when we add this and this together, we get a positive numerator. Let me put something else up here. Okay, so I've got a little bit more on the screen here than was on there before. We're looking at the function sine hx, which is this function here, and the function cosine hx, which is this function here. We factored e to the x out of the numerator for both of them, and when we do that, for the sine hx we get 1 minus e to the minus 2x, and for cosine hx we get 1 plus e to the minus 2x. So going back to this graph of y equals 1, right, this line right here, and its relationship to the graph of y equals e to the minus 2x, which is this decaying exponential here, knows that when x is 0, the graph in blue of y equals e to the minus 2x starts to be below the graph of y equals 1. And so when x is less than 0, so we're looking at the sine inverse graph, right, for this section, when x is less than 0 and we're subtracting e to the minus 2x from y equals 1, this function is much bigger than this function, and so we have that this part is less than 0, e to the x is always positive, and so we get a negative number for that. However, when x is greater than 0 and we're subtracting e to the minus 2x from y equals 1, e to the minus 2x is, as we said, below 1, and so in that case this is positive. When we go to examine the signs for cosine hx, we see that everything is positive, right? E to the x is positive, the 1 is positive, e to the minus 2x is positive, and so we get a positive sign in both places. So the sine h function is negative when x is negative and positive when x is positive. The cosine h function is always positive. So let's summarize that here on this page. So I've got here on this blackboard the function cosine hx, which is always positive. And if we go back and look at its graph, we see that the graph of cosine hx is always positive. And then we look at its derivative. Well, when x is less than 0, it has a negative derivative, so it's decreasing. And when x is greater than 0, it has a positive derivative, so it's increasing. Go back and look at the graph, and we see that, yes, on this section right here, it is decreasing, and on this section right here, it is increasing. And then over for the second derivative, we see that's always positive, which means that it's always concave up. And we go back and look at the graph and see that it is bowl-shaped up, and so yes, it is concave up. And now we're going to do a similar analysis for the sine h function. The sine h function is below the axis when x is less than 0, and above the axis when x is greater than 0. That is what we have happening here, right? It's below the axis here, and it's above the axis here. Its derivative is always positive, so it's always increasing. And yes, when we look at its graph, that is an always increasing function. And then finally, its concavity, it's concave down when x is less than 0, and it is concave up when x is greater than 0, and the graph of the function is concave down on this section and concave up on this section. So we've done the derivative analysis for the functions cosine hx and sine hx. On a test, I wouldn't hold you responsible for this derivative analysis that we did on these two, what's below this graph and this graph itself, but I would want you to, when you label or when you graph cosine hx and sine hx, put in its first and second derivative information in labeling the graphs. Okay, so we've got these hyperbolic functions and looked at the graphs of them. Now we want to look at the inverse hyperbolic of these hyperbolic functions and see what kind of derivatives they lead to. So in your book on page 156 and 7, you see derivations for the derivative of the hyperbolic sine inverse and for the hyperbolic cosine inverse. In class we'll also do it for hyperbolic tangent inverse. So let's go through this for y equals hyperbolic sine or hyperbolic sine inverse. So as before, we're going to take the sine h of both sides to get rid of the inverse. So we have sine h of y equals x, which we'll rewrite as x equals sine hy. We're going to then write that as what the hyperbolic sine is e to the y minus e to the minus y over 2. We're not going to do the dx, dy dx in terms of 1 over dx dy. We're going to solve this directly for y. So first thing we're going to do is multiply everything through by first by 2, and then we're going to multiply by e to the y. So first we multiply by 2 and get 2x equals e to the y minus e to the minus y. Then we multiply by e to the y, so this left side becomes 2x e to the y. The right side, first term is e to the y times e to the y, which is e to the 2y, so this is e to the 2y. The other term on the right side is e to the minus y times e to the y, which is e to the 0, which is 1. And now we're going to rewrite this in sort of a descending order, e to the 2y. We bring this term right here over to the right side, and it is then subtracted, and minus 1. So we're setting it up as if it's a quadratic, and actually is a quadratic if we say let e to the y, or let z equal e to the y, then z squared is e to the y squared, which is e to the 2y. And so we take where we left off, and it turns into what in the variable z? It is z squared minus 2xz minus 1 equals 0. And we're going to apply the quadratic formula to that. So z squared minus 2xz minus 1 equals 0. We're solving this using the quadratic formula in the variable z. So this right here is the coefficient of z, or actually the minus 2x is. And so it is negative b, so the negative of 2x, plus or minus the square root of b squared. So we're squaring minus 2x, which gives us 4x squared, minus 4ac over 2a. And so if we clean this up, we get 2x plus or minus. Now let's take a look at what we have here. This is the square root of 4x squared plus 4, and so we can take a 2 out of that, or take a square root of 4 out of that as a 2, and so we can simplify this like this. Everything divided by 2, And so z is x plus or minus the square root of x squared plus 1. And remember that z was e to the y, and the minus term turns out to be one that we can throw away because this expression right here is bigger than the expression x. Because if we think about it as if we ignored the plus 1, square root of x squared would be x, but since there's a plus 1 in there, under the square root of that term is bigger than x. So this term right here is bigger than x, and so we can throw that away because e to the y is always positive. And so let's say that our z, which is e to the y, is only this solution of the two possible solutions, and we can take the ln of both sides. The ln of e to the y is just y, and then we've got ln of this, and on simplifying we've got y equals ln of x plus the square root of x squared plus 1. So what have we accomplished getting it to this point? Well, if we go back, we were trying to find the derivative for this, but we didn't know how to do that because we didn't know what sine h inverse was. But we found a way to rewrite sine h inverse, right? Remember, sine h inverse is y. And so by rewriting it this way, we can take its derivative using the formula that we know for differentiating the logarithmic function. It is what the reciprocal of the function times the derivative of the inside function. What's the derivative of the inside function? The derivative of x is 1. And the derivative of that square root function is, what, 2x over the square root of x squared plus 1. We're going to multiply the top and the bottom of this by square root of x squared plus 1 over itself to change it from a complex fraction to a fraction that's not a complex fraction. In other words, it gets rid of this denominator, and when we do that, what do we get? Okay, so let's do this multiplication. So remember, we're distributing this across here, so we get what? Square root of x squared plus 1, because we're multiplying it by 1, and then we cancel with the denominator, so we get this, and in the numerator, actually I had a mistake here. This we take this derivative, there should be a 2 here, so these 2's cancel, so this here would just be... Okay, so we're going to do this multiplication. There was an error here. There should have been a 2 down here in the denominator when we took the derivative, so that 2 cancels out with this 2. So we're going to do this multiplication by square root of x squared plus 1 over itself. We multiply it first by 1 and get this, and then we multiply it by x over square root of x plus square root of x squared plus 1. The square root of x squared plus 1 cancels out, right? And so we just get x, and then in the denominator we get, if we don't multiply it out, we get x plus square root of x squared plus 1 times the square root of x squared plus 1, and we leave it in that form because then we notice that this term in the numerator cancels with that term in the denominator, so we're only left with this. And this is our y prime, and y prime is sine h inverse of x's derivative. So this, in its derivative form, is another important integral structure. When we have square root of x squared plus 1 in the denominator, we can integrate that and get sine h inverse of x plus c. So you see this same derivation in your textbook on page 156, and notice that also on page 157 we go through it for cosine h inverse, or at least partly for cosine h inverse x. The only difference there would be what? That if we were doing this same derivation to find the derivative of cosine h inverse x, there would be a plus sign here, and a plus sign here, and a plus sign here. And if we go through all of those steps, you see that the result for cosine h inverse is very similar. So we put it on the same screen. So cosine h inverse of x's derivative is 1 over the square root of x squared minus 1, and its corresponding integral formula, of course, would involve square root of x squared minus 1 in the denominator. And then the final derivation from the section for tangent h inverse derivative is going to be a problem that will work together in the classroom. So this concludes this video for section 5 in the text, and it concludes the videos for this chapter, with possibly some more videos to be added with some examples of problems from class where we had difficulty.